Thank you. So I've slogged around quite a few years on Casper Creek, and one of two of my most memorable moments was when I was on a storm duty, December 28, 2005, and I got a radio transmission from the crew downstream. It wasn't a telephone, it was a radio. You better get down here. This is something you're going to want to see. So I get down to the confluence, and I just see the muddiest, brownest water pouring out of the tributary, and hustled up to where I saw that our upstream flume, Eagle, had been taken out by a massive landslide. And in fact, it was the largest landslide we've seen in the history of the experimental watershed, about 5,500 cubic meters. And of course, it was my husband's birthday to boot, so what a present. And the page down is right there. All right, so we know that large landslides move a lot of sediment. They enhance turbidity, and they can have a lasting effect on channel form. A lot of what we know about the effect of landslides on channel form in the Redwood region comes from the work that was done in Redwood Creek by Marianne Mayday, Vicky Osaki, and others on that team. But how persistent are the changes associated with these landslides is something that we're still trying to get our minds wrapped around. We know that slide scars revegetate slowly. We know that the soils redevelop even more slowly. And seemingly stable deposits can remobilize during large storm flows even decades later. In the yellow there is Robert Horvat. I don't know if he's in this talk, but he was my buddy for that storm, and he's certainly at the conference here. So in order to evaluate cumulative watershed effects, we need to better understand the persistent influences of prior landslide activity. We have long-term data from the Casper Creek experimental watersheds that allows for an evaluation of the temporal distribution of sediment inputs after individual landslide generating storms. We have sediment routing data that are also available to explore the impacts of particular landslides over time. So we're in coastal Mendocino County. The experimental watersheds are comprised of the North and South Fork. Both are about 500 hectares in size. They were established in 1961 to mostly look at the impacts of logging on streamflow and sedimentation. They were originally harvested more than a century ago. The geology is coastal belt Franciscan sandstone and shales. Soils are typically loams, gravelly loams at the surface, and downward water movement is impeded by a clay-rich subsoil. We have a mean hill slope gradient of about 25 degrees, and the average precipitation is about 1,200 millimeters per year. So the map on the right displays the locations of the large landslides we'll be talking about during this talk. Our data set of landslides includes those that were inventoried and surveyed, and we make these surveys on at least an annual basis. In the North Fork since 1986, and on the South Fork since 2000, when our network of tributary gauges was installed. So at a minimum, we have slide location, dimension, and the volume of material that was displaced. And those were recorded initially on paper form, but then we developed a GIS database. And for the largest landslides, we also have traverse data and topographic surveys. For channel surveys, we document changes in sediment storage and channel form. Specifically, we have 60 main stem cross-sections on the low gradient main stems, about 2,500 meters on the North Fork and the South Fork each. And we try to survey those every other year. In addition, for this project, we established 6 cross-sections on the Eagle tributary below that large landslide I mentioned at the start of my talk. And we have other Yeah, not a show. And we have other cross-sections on South Fork tributaries that were established to look at the effects of some decommissioning work that went on there in 1998. We also have a thaw wave profile of both the main stem and up the Dollard Eagle tributary, and we have periodic measurements of steps, which are organic debris dams. For our definition, they're at least 1 foot high and stored at least 5 cubic feet of sediment, and these were done annually up till 1995, and then just 2 more times since then. Actually, it should say 2006 and 2016. So on both the North Fork and South Fork, we have a network of gauging stations, and they measure flow and turbidity at 10-minute intervals. We also operate automated pumping samplers to measure suspended sediment concentration. Andy already talked a little bit about that methodology, but I will add that our load estimation methods, we derive load estimates by regressing sampled suspended sediment concentration on the flow and turbidity record for individual storm events at individual locations. And in one case, we had to derive the load from as the difference between above and below gauge. And those gauges were only 100 meters apart. So this slide has our data set, which includes 11 slides that displaced at least 100 cubic meters material. There was only one large slide on the South Fork in this data set, and there were only 3 slides that were greater than 1,000 cubic meters. So all of the slides are shown in the left graphic, and they are partitioned according to their slide mass. The right or right center graphic shows the, get that out of the way. This shows the same slides, or actually the smaller slides, so you can get a better idea of the scale that we're looking at. So we found that about half of the displaced volume remained on site, and up to 23% was exported as suspended sediment during that storm or that same wet season. And on average, another 7% was exported from the site in subsequent years. And we found that, well, we decided to look closer at 3 particular landslides. 2 of them were the very largest landslides, Z95 and E06, and the third was on South Fork. And even though it was a smaller storm, it was one that delivered a lot of material directly to the gauge and to the stream. And we had pretty good gauging station records for all of these. Okay, in order to estimate excess suspended sediment, we first had to develop the pre-slide relationship between the storm load at the slide-affected gauge and those at the 3 control watersheds. So that's your left graph. Second, then we use this relation to calculate the expected storm load at the slide-affected gauge for the period after the slide. And then finally, we subtracted the expected from the observed to get 3 estimates of excess storm load at the slide-affected gauge. So then we accumulated these through time, and those are the 2 plots you see to the right. And to summarize the results, we averaged the comparison between 3 separate controls. Is that clear? In the case of the Z95 slide, there was no slide-affected gauge per se, so we calculated the excess as the difference between the above and the below. But again, we were able to put together a cumulative curve of the amount of suspended sediment that exported from these individual slides. All right, so here we're looking at the temporal distribution of that excess sediment for the slide U6, and these are deviations from predicted as a function of time and storm size. So this was a pretty interesting finding that the small storms apparently recover within about 8 years. For the 1-year recurrence interval storm, it would take about 15 years to recover. And for larger storms, Our results, of course, are more speculative. After the 2006 slides, the largest storm we've seen was a 1.7 recurrence interval, and we had that in 2008. That one went into this prediction, but the one that we had in 2016 did not go in, and so we tested it, and it was an encouraging result to see that that excess load plotted only 3% different from our prediction. So in the decades since these 2006 slides, Keppeler has seen several drought years, and the flows, the peak flows, have been pretty modest, nothing larger than a 2-year event. So the excess loads that would be predicted in a typical flow regime would be a lot higher than what we actually saw during the time span of our study. And suspended load is only part of the story. We don't measure bed load directly, and I have to acknowledge there's considerable uncertainty about how to measure about how coarse sediments will break down as they move through the channel and move downstream. We do have measurements of channel deposition to add to our story of how landslides influence channel condition. Here are the main stem cross-section changes. We limited our assessment only to those slides that delivered more than 100 cubic meters. Remember from the earlier slide, a lot of our storms didn't deliver that much sediment. And they also had to have downstream cross-sections. We generally had 4 to 8 cross-sections below the slide confluence, and we just interpolated between them to figure out a volume that accumulated in the reach. The slides here are listed from largest to smallest, and you can see by the yellow highlighting where aggradation exceeded 5 cubic meters. So in general, it's the larger landslides produce the most aggradation. Large woody debris is also a pretty important part of this story, and I would encourage you to check out my co-author Sue Hilton's poster this evening to learn more about how large woody debris is affecting things at the Casper Creek site. And then the other thing I would say is that the U6 slide is a bit of an anomaly. It actually scoured after that landslide deposit. And there's another story behind that, too. We had several large mass wasting events in 1999, and that sediment is probably still moving through that main stem reach. So what was already there and is moving through was scouring, and that was a bigger effect than what came from the new landslide. Complicated cumulative effects. All right, so U6 did result in deposition at the decommissioned road crossing above the main stem confluence. So this is up in the tributary. And here, if you look at the photos from right to left, you can see we had a pretty good gully before the slide came down, and then that gully filled with slide material, and then that slide material started excavating, and by year 5, which is when we finally got around to actually surveying the cross-section, I think it was about half of what the original volume was. And that's really just based on photographic evidence. All right, so the slide I mentioned at the start of the talk is really comprised of 3 components. There were 2 slides, I'm pretty close, and a debris track, and we mapped 6 deposits downstream. So if you look at the smaller map in the upper left, you can see the purple blotches of the landslides, and you can follow the track down. We had 4 downstream gauges, including the Eagle gauge, which was the one that was damaged, destroyed by the slide, by the debris flow, and Dollard, which is the one where we were able to do most of our suspended sediment measurements during that storm. And we have comprehensive data on channel condition for this slide as well. We have the fall wag profile, which you see here, and cross-section changes and step storage changes. So the orange squares are the depositional features relative to where the slide came in. And we saw an increase in the fall wag elevation of 33 centimeters on average, and that's for the upper 400 meters of the reach. And the deposition was as high as 4 meters, and that is where the slide back entered the tributary channel. So between this and the cross-section results, we have a pretty good idea of what kind of volume that slide debris was deposited, what kind of volumes were deposited. So now we're looking at a close-up of that same slide track, and we see the 4 distinct depositional reaches. The largest was at the base of the debris track, 1,000 cubic meters. Right below that, in what I call the valley bottom at the confluence of the slide track, we had about 700 cubic meters. And below the flume, a smaller tongue of the debris flow deposited sediments, a couple hundred there, and then there was another couple hundred further down. The first 3 we do have good cross-section data on. We have cross-section data on. The last one we don't. So the changes of those cross-sections showed just continued activation just for the first couple of years at the very top site. So we reasoned that the slide scarp was still producing some sediment, still exporting sediment before it revegetated. But by year 9 or 10, scour was more dominant all across the board. The one exception being Site C. And Site C, we did see some aggregation, but that is attributed to some new woody debris that is trapping additional sediment. Meanwhile, the suspended load story is kind of interesting here because the loads actually started to decline. And we reasoned that these debris dams, particularly B, is actually trapping suspended sediment in the upper watershed. About half the watershed is above that point. In contrast, at the gauging station downstream, Dollard, the suspended loads remain elevated, and there is substantial head cutting and channel widening going on there, and we think that these processes perhaps were aggravated by the slide. How am I doing? 2 minutes. Okay, well, the step storage ended up being a pretty small part of the picture. It is kind of interesting, but we don't have time. So I will get to the conclusionary part. We pieced the whole story together. So here's the whole enchilada, beginning at the scarp, about half the slide volume deposited at the confluence with the tributary, another 10% deposited between Eagle and Doll, a little more on the main stem, and another 10% in the weir pond. Meanwhile, for suspended load, about 15% of the total slide mass was carried in the suspension to the weirs, where about 5% dropped out before spilling over the weir dam. So in conclusion, the displacements greater than 1,000 cubic meters were most influential in terms of both suspended transport and channel form. Location matters, hill slope position, and proximity to the stream gauge were key factors in our ability to detect the effects of smaller slides. And legacy roads and skids contributed not only to the genesis of one slide in particular, but resulted in unimpeded delivery of that slide material to the stream channel. The excess sediment loads diminished within 8 years for smaller storms, but they might endure for much longer for larger storms. And this is all part of a bigger, larger cumulative effects question about background sediment production rates, which are going to reflect the ancient and the recent landslide activity, hydrologic regime, that's your storm pattern, and human-induced alterations of hydrologic function. And all of these need to be considered. Our third experiment for Casper Creek is underway, and we are addressing some of these sediment sourcing and hydrologic change issues in further detail. And we have a poster on that this evening. Thank you.